Hey guys, welcome back. And today we are going to be doing some parametric equations and its relation in differentiation. So first of all, I'm going to begin by explaining some basic pointers about how to recognize parametric equations, okay? So firstly, the word equations means plural, and parametric equations tend to occur in pairs. So you usually have like two equations always popping up together. Another thing about parametric equations is that they are connected to each other by a common variable. All right, and in a lot of questions, you'll notice that that variable tends to usually be the letter T. All right, now when it comes to parametric equations, that third variable is called the parameter. All right, it's called your parameter, parameter, however you want to pronounce it. And you can actually find the value of your differential dy with respect to dx, even though you have a third variable being presented between both equations. So let's go ahead and see some of the basics. Okay, so I'm going to start with a first equation. Let's just say we have x being equal to 3t to the power of 4 minus 1. And let's have a second equation, y being equal to 5t squared plus, let's just say, t to the power of 4. All right, so you can see on screen we have 1 and we have two equations. So, I mean, they could be simultaneous even though they have that, a lot of more variables. But the thing is, how do you differentiate simultaneous from those parametrics? They usually have that third variable, the parameter t, being present. And in parametric equations, you would have more than likely one of your equation x in terms of t and the other one y in terms of that common variable t as well. Now, as you would any normal differentiation, you would observe what you have on your left hand side. And in the first equation, we'll be differentiating x with respect to t on your right hand side because we have the variable t on the right, not y. And we do not have x on the right hand side instead, as typical equations come in this form, right? So just take note of that. When you're setting up your differential, make sure you observe what is on your left and your right hand side before you begin differentiating. All right, so now that that's cleared up, we can go ahead and differentiate this first equation x with respect to t using our basic rules. That'll be 4 times 3 gives us 12t, and we reduce our power by 1. The differential of a constant is just 0, so -1 differentiated gives us 0. And we're done. That's pretty much it. Similarly, we would go across to our second equation, and we can see clearly that we are differentiating y with respect to t. Using our standard differential rules, we will multiply that coefficient 5 by our power to get 10. We will rewrite that variable t and reduce the power of 2 to 1. And then instead of writing that power 1, it's understood to be there, so we're not going to write it. Follow up with your addition sign, noticing that your second term is a powered variable, so we will have some component remaining. After differentiation, you would end up getting simply 4t to the power of 3. Okay, so what happens after we have found values for dx dt and dy dt? How are we going to find that final dy dx? Well, that's where something called the chain rule comes into play. All right, so I'm going to highlight our chain rule. And a chain rule is not something that is necessarily memorizable. You can create it just by using some basics of cancelling. You see, if you're in your numerator, you want to have dy, and if in your denominator you would like to have dx, then after multiplication of two fractions, if you want to call it that, then these terms here and here should essentially cancel each other out, such that we get back what we want, which is dy on the top and dx on the bottom. So how can we do that? By keeping true to what's given in the question. Now if you look, you'll notice that we have the variable t, and we differentiated t to get dt. So that missing component on the top and bottom crisscrossing each other is actually dt. And in essence, they essentially cancel each other out. So it works. Now, after you have created your chain rule, which is this within those bars there, then you can go ahead and simply utilize what you have done into your chain rule to find dy dx. It's just basic substitution. So we will go as follows. Dy dx is simply equal to, let's find out what dy dt was. Dy dt was 10t plus 4t to the power of 3. And what we're going to do is make sure we include brackets so that our answers is not affected. Then we have a multiplication sign, followed up by dt dx. Now if you look across here, you'll notice that we have dx dt and not the vice versa. So what you can do is from dx dt, you can flip it and you can get a value for dt dx. It will always be 1 over whatever you got. So finally, we can substitute that value for dt dx into our chain rule. Now for this reason, you will frequently see that instead of a multiplication for the chain rule, some textbooks have it written as follows. Dy dt divided by dx dt, which is essentially the same thing as multiply by dt dx. Note that when you're dividing by something, you have to flip. Alright, so you can memorize either of these chain rules, or you can choose to generate it on your own. Now finally, let's clean up this answer. So I'm seeing we have a denominator and a numerator, so I'm going to write it as follows. Now you can leave your answer by that, but at this stage I'd say we have enough knowledge to understand how to factor out common terms, common numbers, common variables. So let's try to factor out what we can see is common with both the numerator and denominator. On top, I'm going to factor out 2t. That will leave me with 5 plus 2t squared. On the denominator, if I factor out 2t, I will just end up with t squared. Continuing, it's just a simple matter of cancelling those commonalities, and there you have it. That's your final answer. So dy dx was found to have a value of 5 plus 2t squared all over t squared. Take note that you cannot cancel t squared with the above 2t squared unless you also separate it with the 5. So if you wanted to split that up, it would actually be 5 on t squared plus 2t squared on t squared, which cancels down to 2. So please take note of simple separation of terms when it comes to having a denominator present, and not making mistakes in thinking you can cancel crisscross when you have an addition of terms on the numerator. Okay guys, now one possible thing that can also come when you have finally gotten a value for dy dx is that sometimes they can ask questions like these. Find the value of dy dx when t has a value of 1. Now, in a case like this, you might think this sounds difficult, but you must remember all of these equations are for a curve. So all they're asking you is that at the point and time when the parameter t is equal to 1, what's the gradient? And because you already have found an expression for your gradient, dy dx, and it was actually in terms of t, I'm going to use a simplified version here, then you can simply say at time t equals 1, or your parameter t equals 1, it will simply imply that your value for your gradient is going to be equal to 5 on 1 squared plus 2. 5 on 1 squared is simply 5. 5 plus 2 gives us a value of 7, and that's it. So at t equals 1, we found that the value of dy dx was indeed equal to 7. Now take note that for parametric equations, even though it seems very straightforward, I just want you guys to be aware that you can also have parametric equations in terms of trig functions. They can literally be in terms of exponential functions. They can come in any nature. For example, you can have situations where you're giving a parametric equation such as 2 sine of t, and then the other associated parametric equation could be y is equal to cos of 2t. All right, so these two variables, the two standard variables present are always x and y, but you can see that they're connected by that common parameter t. So once again, you would go ahead and you would differentiate the first one with respect to t. You would differentiate the second one, y, with respect to t. And then you would utilize that standardized chain rule to find the value of dy dx. All right? And you can use the multiplicative format if you want, or you can use the one where you divide by dx dt. It's all up to you. All right, guys, so stay tuned. Up next, I'm going to show something for students who are doing pure maths in Form 6 and upper school, high school math. It's finding the second derivative for parametric equations. So if you guys are just doing like add math, you can stop here. That's all you need to know for now. But if you have plans and you want to know more, and also you're in Form 6, then keep watching the video. Okay, so on screen you can see we have the typical two parametric equations, and in this case they're asking us to find d2y dx squared. You can recognize by the power given there that they were asking us to find the second derivative. Now generally, when you have found a value for dy dx, if you are asked to find d2y dx squared, all you usually do is differentiate that a second time with respect to x. And that is how you end up getting d2y dx squared. But how do you differentiate dy dx when it's not in terms of x? Well, stay tuned and you'll see yet another extension of the chain rule as we work together to get that value for d2y dx squared. So I'm going to work step by step here. So I'm going to take that first equation and we are going to work out the value for dx dt. Differentiating, we will get 2t plus 5, and on the right we will get dy dx is equal to 3t squared plus 3. Now we are going to use our basic chain rule for dy dx, which is dy dt divided by dx dt. All right, using this formula, let's substitute our values. So we can see that dy dt, oh, see, I saw my mistake. That's supposed to be dt. There we go. So I can see that dy dt turned out to be 3t squared plus 3. And we're going to divide that by, well, obviously, dx dt. Now, based on which chain rule you use, automatically it will get placed on the denominator. If you're using the multiplication, even if you flip it, it still gets placed on the denominator. I can see that we have nothing that's in common that we can factor out. So for dy dx, that's our final answer. Now, let's move on to finding a value for d2y dx squared. So essentially, what we have found over here is dy dx. And usually, after we find dy dx, what we do is differentiate that with respect to x a second time. But in this case, you can observe that all the variables present are actually t on our right-hand side. So if we were to differentiate dy dx, it would actually be with respect to t. Now, in order to accommodate what's taking place in this question, what we need to do is get rid of that component of t and introduce a component of dx so that we can get that dx squared. This is where the chain rule comes into play. You can cancel out that dt by multiplying by dt, and you can introduce your dx by multiplying by dx on the denominator. It works as follows. In the end, these two would cancel such that you would get back your d2y on dx squared. So pretty much all you need to do is differentiate your dy dx, but instead differentiate it with respect to t, and then remember at the end to multiply by dt dx, which you would have found initially upon your first differential of your parametric equations. Also take note that because we have multiplication here, some students also prefer to have or memorize their chain rule as follows. So you can differentiate with respect to t your dy dx, but instead you can divide by dx dt. And pretty much that's it. So let's go ahead and do this question on screen. So our value for d2y dx squared, and please make sure you follow up with what you're finding. Don't just put nothing on your left hand side and then follow it up with an equal sign. An equation needs to have two sides. So take the necessary time and bring down your d2y dx squared. Let the examiners and markers know exactly what you are doing and that you understand how your sentence flows. Okay? So we are going to differentiate with respect to t dy dx. And dy dx is a big chunk. It's 3t squared plus 3 all on 2t plus 5. And then at the end, we are also going to have to remember to multiply this by dt dx. Now, because we can see in brackets there, we have a very long chunk to differentiate, you can clearly identify that we are actually going to have to apply the quotient to differentiate what's within brackets there. Okay? So when I differentiate what is within brackets here, I will get d2y, I'm going to do it all in one. d2y dx squared is going to be equal to, differentiating this with respect to t, we're going to get, for the quotient rule, you're going to get v squared on that denominator, subtraction sign. Then you're going to have v over here, 2t plus 5, and the derivative of the numerator, which is 3 2s is 6t, subtract u, which is 3t squared plus 3, multiply by the derivative of that denominator, which is 2. Now, after you have completed that, you can take your time on your own and you can go ahead and you can simplify this chunk. But I'm going to continue working and following along with what I have here, and I'm going to also multiply by dt dx. All right, so dt dx was actually 1 over 2t plus 5. So let's go ahead and clean this up. Like I said, you guys can simplify that on your own. The numerator should work out to be, I believe, 6t squared minus 6 plus 30t. And then you're going to have all over 2t plus 5 squared. And then we're going to bring down our multiply by 1 on 2t plus 5. You can see that we have similar denominators here, so we can simply clear that up to look as follows. 6t squared minus 6 plus 30t all over 2t plus 5 to the power of 3. Okay, so if from the red box to the blue box you did not get what I have, just double check if you may have expanded your brackets by mistake, wrongly. If you forgot a little 2 in between, you know, we all make mistakes sometimes. And essentially, if you made a hit and miss in expanding those red brackets, don't think of it too much because that's algebra, right? You can work on your algebra skills, but the topic is differentiation. So if you were successful in differentiating, be very proud of yourself. Okay, guys, these things can be very challenging sometimes, and I think we get ahead of ourselves and we tend to beat up ourselves too much. So yeah, if you guys got what is on screen in blue, that's the final answer. So it's simple. Once you have found dy dx, let me just go it over one more time. You simply differentiate that a second time, and it's usually going to be using the quotient rule. You differentiate it a second time with respect to t. And then to get rid of that t component, you simply multiply by dt dx. And that's pretty much it, guys. So that was finding the first and second derivative of parametric equations. Of course, in exams, you're going to have exponents sometimes and trig functions sometimes and so on. But I hope you guys were able to understand the second. If you guys want a topic, this is called the second derivative of parametric. I kind of have like a layover in my, I'm not sure if you guys are going to get that in the video, but it's like a delay while I'm writing. So my laptop's probably tired. So this is a second derivative of parametric equations. All right, guys. So good to be with you. Stay tuned. I have more videos coming. I think I'm on a roll today. So all the best. Bye.